In this video, we're looking at question 6 on practice exam 3-1 in the fall 2021 semester in Chem 1211. And the question is pretty straightforward, pretty short here. What answer option correctly identifies the number and types of nodes for a 6d orbital? Now, as a nugget of testing strategy for a question this short that really involves specifying two numbers, don't even look at the answer options. What you want to be able to do is arrive at the correct answer without even looking at the answer options, because all they do is specify different numbers of angular and radial nodes, and you really can't gain this, right? And so let's think through it based on the fact that we're dealing with a 6d orbital, and we're interested in the number of nodes. So the key piece of information here is that we're thinking about a 6d orbital, any of the orbitals within the 6d subshell. Now, given that high n value and the fact that it's a d orbital, I'm not even going to attempt to draw the shape of a 6d orbital. And in particular, if you're in an exam, a time situation, you're in a time crunch, you're not going to be able to go look this up, right? You're going to need to get to the number of nodes by thinking through analytically how nodes relate to quantum numbers rather than inspecting the shape. So that's really the idea behind this problem. And to get started, we want to recognize a couple of things that we know, things that might be on your crib sheet. So the first thing that we should recognize here is that the number of radial nodes is equal to the principal quantum number of the orbital minus its orbital or azimuthal quantum number minus 1. And I think a better way to understand this equation in more general terms is to first note that the total number of nodes in any orbital, any atomic orbital, is n minus 1, the principal quantum number minus 1. Those nodes can be divided into radial and angular types, with the radial nodes being shaped spherically, essentially at certain distances from the nucleus, regardless of our angle of moving outward from the nucleus. Angular nodes are only at specific angles, and that's why they're called angular nodes. And the reason this formula that we wrote works is that the number of angular nodes is always equal to L, the orbital or azimuthal quantum number. So the total number of radial nodes is all the nodes left over, which is n minus 1 minus L, or as we've written it here, n minus L minus 1. So now that we have those formulas down, which I would encourage you to put on your crib sheet, we need to take this 6d subshell label and unpack it to its corresponding quantum numbers. The 6 out front indicates that the principal quantum number has a value of 6, and the d indicates that the orbital or azimuthal quantum number has a value of 2. Excellent. So now we have all we need to determine the number of angular and radial nodes. In a 6d orbital, the number of angular nodes is equal to 2, directly from the subshell label, essentially, and the L equals 2 quantum number. And the number of radial nodes is n, which is 6 minus 2 minus 1, which last I checked is equal to 3. And just as one last sanity check, 2 plus 3 is 5, and that's 1 less than the principal quantum number of 6 here. So this answer does make sense. And is this a choice? 2 angular nodes and 3 radial nodes. There it is.